Hi, I'm Erin East with Keysight Technologies. In today's installment of the Oscilloscope webcast series, we are going to take a look at debugging serial buses in embedded designs. We'll look at common challenges using I2C, SPI, and USB buses. If you'd like to skip ahead to something that looks interesting to you, there's an agenda with time tags in the description below. Alex Klimai is the presenter, but he was unavailable for this intro, so let's go ahead and see what he has to say.
During this webcast, I will discuss the differences between serial and parallel data, industry trends and challenges, why an oscilloscope is a powerful tool for debugging serial buses, how to set up serial decoding, using advanced serial trigger conditions, combining serial decode with mixed signal and power measurements, finding sources of noise using the fast Fourier transforms, and probing recommendations. I'd like to quickly talk about the difference between parallel versus serial data transmission before I dive into debugging serial buses. Parallel transmission sends all the data bits at once. This has the benefit of being simple, fast, and easy to decode with a logic analyzer. Serial data transmission, instead of sending all the bits at once on individual transmission lines, are sent bit by bit over a single wire. This lowers the cost by reducing the space, connections, and power. Higher frequencies are also possible due to the less possibility for crosstalk. However, at the same frequency as parallel transmission, serial is slower. It also uses more processor cycles to send the data and is more difficult to capture and decode. In the electronics industry, serial buses are getting used more often in embedded devices. This leads to greater design complexity, especially when a design has more than one serial standard. You may have many chips in your design that use I2C and one chip that uses SPI. For board-level communication, USB is increasingly being used. This can present challenges when implementing on a low-cost microcontroller due to the rapidly increasing number of discrete integrated circuits beyond the space or cost budget. With all these serial bus standards and more entering the market every year, engineers are challenged to choose the right interface. Since serial data is transmitted bit by bit and can be sent asynchronously, it presents a challenge to debug. Engineers need to be able to decode and trigger each frame as they are sent. Before serial decoders, engineers would have to first struggle to capture a single packet of data, then convert the physical layer to ones and zeros. Once they had that, they would have to go to a lookup table to figure out what that data meant. Also, with the ever-increasing push for smaller devices, engineers are challenged to cram everything onto smaller PCBs. With smaller circuit boards comes a higher chance for signals to couple and interfere with one another. Now, why would an engineer choose to use an oscilloscope to debug serial buses instead of a logic analyzer? A scope is not a replacement for a serial bus protocol or logic analyzer, but neither is an analyzer a replacement for a scope. An oscilloscope allows you to view the physical signal layer and perform compliance tests on serial buses. Oscilloscopes also have high repetitive waveform update rates, which are able to capture infrequent bus errors. Using a scope, an engineer can also find and measure analog signals such as an RF burst triggered from a serial message. The downside to an oscilloscope is that you can only trigger off of one event, while a logic analyzer can be set to trigger off a specific set of events, such as 3 consecutive serial data packets with specific data. Logic analyzers are also better at state analysis and finding functional and timing problems. This is a short demonstration of why serial decode in an oscilloscope is an important tool to any engineer working with serial buses. Some engineers use a 2-box solution to debug serial buses, using a scope to look at the physical signal layer and a protocol analyzer for the decoded values. Using an edge trigger on the scope, with the trigger out pulse of the scope into the protocol analyzer, you can correlate the physical signal on the scope to the decode on the analyzer. Here, I've probed the same I2C signal using a scope without serial decode and a USB-based protocol analyzer. The scope is running on a standard edge trigger, and I have channel 3 of the protocol analyzer hooked up to the trigger out of the oscilloscope. Trying to correlate the protocol analyzer decode and the analog signal on the scope can be a difficult task. Under these conditions, the engineer has no control over what gets triggered. Then, the engineer must somehow time align the 2 outputs. I've done this by taking screenshots of both instruments and aligning them here on the screen. I've performed the same decode using the built-in hardware-based I2C decoder. The location of the decoded hex values corresponds to where it came out of the decoder. This illustrates the power of having a serial decoder built into the oscilloscope. easily being able to correlate the physical signal with the decoded values. Now, I will show you how easy it is to set up a serial decode and how to use the advanced trigger conditions on the InfiniVision oscilloscopes. In just a few steps, you can quickly decode a serial bus. To set up a serial decode, you first need to turn on the decoder. To do this, push the serial hard key, then touch the serial button on the screen and select serial 1. Next, open the mode menu and select which type of serial bus you are probing. Notice the available serial bus decoders in addition to USB, I2C, and SPI. These scopes also support many other serial standards. Everything I show today can be applied to the other serial buses. Next, in the Signals menu, tell the oscilloscope which channel the clock and the data are on for I2C. Any of the analog or digital channels can be used. You would use the digital channels if you know your serial bus signals are working and you are just interested in a logical decode. This leaves the analog channels free for mixed signal analysis. The Signals menu options are similar for every serial bus, but with minor differences depending on the standard. SPI has clock, master out slave in, master in slave out, and chip select. I2C has serial clock line and serial data line, and USB has data plus and data minus. I want to stress the importance of the threshold setting. This setting tells the decoder where to sample the signal and count it as a logical 1 or 0. Here, I've set an incorrect threshold. Notice the decoder fails to properly function and decode across the bottom, and the decode across the bottom of the screen has turned red to indicate the decode failure. Now, I've set the threshold in the middle of the signal, and notice that the decoder is working once again. Some serial bus specs will specify what this should be set to, but a good default if you are unsure is about 50%. This setting is less important for low-speed buses where the jitter tolerance is large. For high-speed buses, this setting becomes more critical. Once you've set up the decoder, the values are displayed across the bottom of the screen in blue, time-aligned to the physical signal. But what if you want to see more information? You can do this by touching the lister button on the top right of the screen. A list of the decoded frames will open up and use half the display. Here, you can see the time of each frame, the I2C reader write address, data, and if the frame was missing the acknowledge. In this case, we know that the read address on hex 29 was not properly received by the slave. If you want more lister information, you can use the full screen by touching the gear and opening the lister menu, and changing the window option to full screen. If you would like more information on a single frame, touch the gear and open the packet view. This will show you all the details for that single frame. You can scroll through the frames using the up and down arrows on the screen to see the physical signal for the packet you've selected. Touch the Zoom to Selection button. You can now see that the scope is zoomed into the hex 29 read frame and that it is missing the acknowledge. Here you can see the different information the packet view displays for SPI, I2C, and USB. USB, being the most complex of these three standards, has the most information to display. Now what if you want to find a specific frame on your serial bus? The chances that you'll find what you're looking for are very low using a standard edge trigger. Sure, you could try to play with the trigger hold-off setting, but that will only get you so far. To find exactly what serial frame you're looking for, you will want to turn on the serial trigger. This is under the Trigger menu, which you can find by either touching the yellow T in the top right of the screen or the hard key on the front panel. Then touch the trigger type and touch Serial 1. If you are decoding two serial buses, you can trigger off of either Serial 1 or Serial 2. Now touch the Trigger On menu on the screen. Right now, the scope is set to trigger on an I2C start condition. Notice all the different I2C trigger options, such as address, missing acknowledge, reader write frames with a specific address, and data. The I2C specification also has specific addresses allocated for EEPROM reads. You could use this trigger to find every time your circuit reads from memory and check what data it is sending. This trigger setup applies to every serial decoder in the scope, but with different standard-specific serial trigger conditions. Quickly take a look at all the comprehensive trigger options available for embedded serial buses. USB has token packets, data packets, CRC errors, and stuff errors, while I2C has missing acknowledge, addresses, write frames, and restart frames. SPI has MOSI or MISO data. Here, the scope is set to trigger on a specific I2C write address at hex 71 and any data. This can show you any data being written to a specific chip in your design. You can also set the values to don't cares or one byte with a specific value and a don't care on the other byte. If you want to know every time your USB design has a CRC error, use the CRC16 trigger. This will show you one CRC error. But what if you want to know every time and how often this error is occurring? You can do this by utilizing a feature called segmented memory. Now, I will show you how you can use segmented memory to find those pesky infrequent serial errors. The standard way a scope's memory is used is by capturing everything around the trigger point. The scope will trigger, then adjust the sample rate to fill the entire time base on the screen. For infrequent serial data, this is not the most useful way of using memory. If you're using a serial trigger condition, you will see that one frame and everything that happens shortly before or after. Most likely, the time before and after your serial frame will be dead bus time where nothing is being transmitted. What segmented memory does is allow you to selectively fill up the memory with only what you want to see based on the trigger condition. The scope will wait until it sees a serial frame that meets the trigger condition, save it to memory, time tag it, then rearm the trigger and wait for the next occurrence. Imagine that each of these pulses are serial frames. In that case, we've cut out the dead time between the frames and we're able to capture more serial information. Let's say I want to capture 400 milliseconds of time on the serial bus to find a particular packet. I've set the time base to 40 milliseconds per division for a total of 400 milliseconds. The sample rate had to reduce in order to fill the entire memory. Once you zoom in on the captured signal, notice it was undersampled and aliased. This is causing the decoder to fail. Now, I will better utilize the scope's memory to find every CRC16 error that occurs on this USB signal. To do this, I will set up a CRC16 trigger, then set the time base and vertical scaling to show one frame. Once you start segmented memory, these are the settings that we'll use for every waveform it captures. The scope will wait until it has seen 500 trigger conditions, and then decode all 500 and time tag when each one occurred after the first trigger. From this, we know that the error is occurring about every 800 microseconds. Notice that the scope was able to maintain a high sample rate of 40.8 megasamples per second. Also notice that the scope was able to capture all these error frames over a period of 400 milliseconds. It didn't have to capture everything over the 400 millisecond period and then have to search for the errors. I only got what I wanted to see. Next, I'd like to show you how you can use the dual time interleave decodability of the InfiniVision oscilloscopes. Here, I am probing USB on channels 1 and 2 and I2C on channels 3 and 4. To turn on the second serial decoder, I will follow the same procedure that I showed before, but selecting both serial 1 and serial 2. You can see here that both USB and I2C are being decoded simultaneously. I've used 4 analog channels, but if you want to perform mixed signal analysis in addition to dual bus serial decoding, you can probe the serial buses using the digital channels. Opening up the lister and setting it to display all will show you the decoded buses in a time interleaved color-coded table. You can see USB here in blue and I2C in green. This is a powerful tool if you have multiple serial buses in a design. Now, I'd like to show you how you can perform mixed signal analysis on an RF burst triggered from I2C. Digital channels 0 and 1 are probing an I2C bus, and analog channel 1 is an RF burst triggered by the I2C write on address 64 hex with data DA. Here, you can see the lister with the decoded I2C packet that is triggering the RF burst. I've zoomed in on the RF burst and turned on measurements. The max amplitude is 1.84 volts. Be sure to vertically maximize the analog signal on the screen. This utilizes the full range of the scope's ADC. This is a general best practice when using a digital storage oscilloscope for the most accurate measurements. If you want to get more in-depth analysis on the signal, you could perform an FFT using the math functions to find out what frequency components this signal is comprised of. Here, I've done just that. I've turned on an FFT on the RF burst. I also turned on the peak finder to automatically find the main frequency components of the RF burst. This signal's main component is 123 kHz with additional components at 1.22 MHz and 11.5 MHz. Notice the serial decoder is still running as indicated by the blue bar across the bottom of the screen, and the lister button in the top right of the screen. Now, I will demonstrate how you can use the FFT function to identify sources of noise on your serial bus signals. Here, I am probing a high-speed USB signal that appears to have quite a bit of noise. The question now is how can I use the scope to find the source of the noise? My first approach is to take a single sweep of the signal and run an FFT. Surprisingly, the noise appears not to be present. This leads me to believe that the source of the noise is a much lower frequency than the signal. To find the frequency of the noise, I will slowly increase the captured time span to catch those low frequencies. Watching the FFT, I still can't find the source of the noise. I've zoomed all the way out to 10 milliseconds per division, and immediately it becomes apparent that the noise is about 60 Hz. Now, what common signal operates at that frequency? AC power in many countries operates at 60 Hz. This tells me that somewhere in my embedded design, there's an AC power input near the signal path of the USB. Now that we've rooted out noise from our 60 Hz power line, what about other sources of noise? Take a look at this signal. The noise appears to be a much higher frequency. Running a single sweep on the signal, you can see that the coupled signal is apparent, but from the FFT, I still can't tell what the frequency is. Zooming out a little bit further on the time base shows me a much more complete picture of the coupled noise. From the FFT, it is apparent that the source of noise is coming from a 16 MHz clock. Having such a dominant signal at a rounded frequency value is a good indicator that this is not part of the digital signal. Digital signals will rarely have a frequency component at a nice round value. Now that we've discovered the source of noise from AC power and digital clocks, let's look at finding interference from a wireless signal. Here I'm showing a good USB signal with no noise sources present. Running a jitter measurement, I find that it has a standard deviation of 111 picoseconds. One thing to note is that these jitter measurements are only available on the 6000X Infinivision oscilloscopes. This USB signal is receiving interference from a wireless LAN end signal. Running the same jitter measurement shows me that this signal has 602 picoseconds of standard deviation of jitter compared to the 111 picoseconds of the clean USB signal. While this doesn't seem like much interference compared to the 60 Hz power or clock signal, it could potentially cause issues in your design. Remember back to the importance of the threshold setting I talked about earlier. Jitter on a high-speed USB signal could cause your device to become inoperable with a host. You can use the same technique I described before to find the source of the jitter. Running an FFT on the signal, I immediately see that the frequency spiked at 2.4 GHz. If you know your design has a wireless signal at 2.4 GHz, then you would want to go check your antenna and USB traces and make sure they're not too close on the PCB. Since the interfering signal was much higher frequency than my serial signal, I did not have to increase the time span to catch it on the FFT. Now, I will demonstrate how you can use the power of segmented memory to figure out how long your USB device takes to enumerate with a host. USB enumeration happens when a USB device is connected to a host. The host has to figure out what version of USB it is and then figure out what the device is. How the speed of the USB device is communicated varies between different USB standards. In the case of USB 2.0 and lower versions, the speed of the device is identified from the voltage level of the data plus and data minus lines. For high speed, the device initially connects as a full-speed device and switches to the high speed after the chirp handshake, which is part of the reset signaling. The high-speed device initially connects as a full-speed device by pulling the D plus line high. Here, I'm using a USB breakout board to probe the D plus and D minus signals of a mouse. Depending on your design, you could either create a USB breakout board like the one shown here, or add probe points into your prototype. Once again, I'm going to start setting up segmented memory by setting my trigger condition, which in this case is a setup packet, and then my horizontal and vertical settings to show one packet. Since I don't know how many setup packets it will take to enumerate, I told the scope to collect 100 segments. After you have that set, turn on segmented memory and connect the USB device to the host. The scope appears to have stopped after it collected 11 setup packets. Now, to decode those packets and complete the measurement, push the Run Stop button in the top right of the scope's hard panel. Once you've stopped the acquisition, the scope will decode and time tag all the setup packets. Here you can see that the USB mouse took 28 milliseconds to enumerate in 11 packets. This test was run on the mouse connecting to the oscilloscope itself, but the enumeration time could vary from one host to another. I've run the same test, but this time on a USB flash drive. This drive operates on a high-speed USB bus, opposed to the full speed of the mouse. Interestingly, it took 371 milliseconds to enumerate with the oscilloscope as a host. With my PC as the host, the flash drive took between 700 and 800 milliseconds to enumerate. Each time I ran the test, I got a different result. If you're putting together a datasheet of typical enumeration times, I would run the test many times and either state a range or an average. Now that you know how long your USB device takes to enumerate, you'll want to know how much power it is consuming. Power is increasingly being scrutinized in low-power embedded designs, especially in battery-powered applications. Once again, I'm using the USB breakout board, still probing D+ and D-, but also added a voltage probe to the 5-volt power rail and an inline current probe. The N2821A current probe I'm using is unique due to the use of a sense resistor. Since it is not measuring a current loop, there's no degaussing or zeroing required. This probe can also measure currents as low as 50 microamps all the way up to 5 amps. You can see channels 1 and 2 on D+ and D- with the decoded USB in blue across the bottom. Current is in red and the 5-volt rail is in blue. I've turned on the math function and multiplied the current and voltage. The scope knows that current times voltage is power and displays it as such. Interestingly, note the voltage droop during the current spike. When an optical mouse is idle, the sensor is pulsed to save power. When I start moving the mouse, the current and power consumption increase for accurate readings. During idle, the mouse consumes 113 milliwatts, while it consumes 235 milliwatts during movement. You can see this happening in the animation. Now what if you have a serial bus that is having intermittent random errors? I will show you how you can use the zone trigger to isolate the source of the problem. Here, you can see a USB signal which is having intermittent errors from a coupled transient signal. But how can you isolate it? Using traditional digital oscilloscope trigger techniques, it would be very difficult. To isolate the signal, all I had to do was draw a box on the screen with my finger where the transient was appearing. This is a great demonstration of the power of a touchscreen on an oscilloscope. I was already using the USB startup frame trigger, and adding the zone trigger tells the scope to only trigger if it sees a USB startup frame and a signal in the area that I drew on the screen. You can also use the zones to only trigger a scope when something doesn't intersect with the zone. Using the zone trigger, you can also combine other serial triggers and draw a zone on a specific bit if you only wanted to see a frame when that bit is present. Let's say you've designed a product that implements USB, and you want to quickly be able to check if everything is meeting the specification. This is where compliance tests are useful. Most low-speed serial buses don't have defined compliance tests due to the loose jitter specifications. Almost all high-speed buses have a defined compliance test where timing and jitter is critical. To run a compliance test on a high-speed USB device, I'm once again using the USB breakout board, but this time I'm probing D+ and D- with an active differential probe. The minimum bandwidth required for a high-speed 480 megabit per second USB signal is 1.5 gigahertz, which will capture up to the fifth harmonic of the signal. To set up the scope for a compliance test, you want to trigger on a data packet and maximize the signal on the screen. Maximizing the signal on the screen will utilize the full range of the ADC for the most accurate measurements. Under the test menu, you can select which type of compliance test you want to run. In this case, I'm running a test on a flash drive, which is a high-speed device. High-speed electrical tests are performed either near-end or far-end depending on the configuration of the product. The terms near-end and far-end are based on which end of the cable the test fixture is attached to in relation to the device being tested. The point where measurements are made dictates what eye template is used. Near end, the test is run at the peripheral's receptacle. Downstream tests on ports on hosts and hubs are always performed at the near end, as are all peripherals with a USB-B receptacle. For far end, the test is run at the end of the cable. Devices that have a captive cable are always tested at the far end. The test results will open in a form with an easy-to-read, color-coded pass or fail and show the eye diagram. It will tell you the end of packet width, which is 7.88 bits wide. The measured signal rate, in this case, is 479.8 megahertz, what the edge monoticity is, and what the rising and falling edge rates are. Additionally, it will measure RMS jitter on the signal. Finally, I'd like to quickly discuss serial bus probing options. Probing low-speed serial buses can be done easily with the scope's included passive probes. The only downside is that you're limited to 4 channels. Another option is to use the digital MSO probes, which will free up the analog channels for mixed signal measurements. However, you can't use the digital channels for differential buses or running compliance tests. To measure differential buses, you can either use an N2818A or an N2750A active differential probe. For performing measurements on high-speed USB signals, you need at least 1.5 GHz on your active differential probe. Today, I've shown you many tips and techniques for debugging serial buses in embedded designs. Hopefully you're able to take what I've demonstrated today to quickly isolate and solve your serial bus issues. All the examples I showed today were done on an InfiniVision series oscilloscope, which range from 70 MHz to 6 GHz. We also offer the Infinium scopes, which go all the way up to 63 GHz. Here, you can see the serial options on each of the InfiniVision oscilloscopes. For more information on debugging serial buses, be sure to check out our application notes and videos available on Keysight.com. If you enjoyed this webcast and would like to learn about more topics, we have many recorded webcasts that you can view on demand at any time, as well as upcoming live events.
Now, on to our question and answer session. Our first question is the waveform update rate important for serial bus debugging?
Yeah, waveform update rate can be very important for debugging serial buses, especially if your serial buses have those infrequent transients, like I showed earlier in the webcast.
Okay, thank you. The next question is, in terms of segmented memory, can I scroll through the segments?
Yes, once you've captured all that, you can scroll through all the segments and then take a look at the signal for each segment and the decoded value.
Okay. Do you have any USB 3.0 validation techniques?
Yes, we have comprehensive USB 3.0 and 3.1 solutions.
Okay, the next one is it possible to use single-ended passive probes for USB?
Yes, it's for low-speed USB buses, it's completely possible to probe the D+ and D- using the passive probes. I showed that in the webcast earlier. But for higher speed, when you start needing active probes, you need to go with the differential.
The question that I just asked, I guess my phone dropped out, was what series scope would be able to handle USB and gigabit Ethernet signal analysis?
For USB, both the InfiniVision and the Infinium scopes can be used, but for gigabit Ethernet, Infinium scopes are recommended.
Okay, the next question is, can I export the captured segmented data?
Yes, you can export captured segmented data.
Is there a PCIe protocol decoder in the scope series?
The InfiniVision oscilloscopes don't have a PCIe protocol decoder, but the Infinium series does.
Okay, is it possible to set up a proprietary serial protocol that's SPI-like with MOSI/MISO equaling 8-bit data?
That's something that you would have to check out for yourself and contact Keysight's support representatives.
Okay. Well, let's see. It looks, Alex, like you've answered all the questions. You did a great job. Thank you. I'm going to say that concludes today's presentation. you.